So let's continue with the last lecture. This is regarding tetrahedral splitting. I have discussed about the octahedral splitting in elaborate way. Now this one is tetrahedral splitting. So in case of tetrahedral, the dxy, dyz and dzx will go higher compared to dx square minus square and dz square. That will be comparatively lower. Why? Because here in this case, this approach of the ligand is angular. So this is the shape of tetrahedral geometry. Just think, this is the tripod stand, tripod table. This is tetrahedral. Just think over, this is tetrahedron. Now, the ligand is approaching along angular way like this. If this shape you have to make, this tetrahedral shape, then the ligand must approach angularly. Now the dxy, dyz, dzx are in the plane, and interaction with them will be higher. And those who are on the axis, interaction of the ligand with them will be less, because they are on the axis, but the approach is angular now, not on the axis. Okay, what is the main difference between octahedral and tetrahedral geometry? In case of tetrahedral geometry, the ligands are approaching angularly, not along the axis. And that's why the repulsion with the dxy, dyz, dzx will be more, and it will be less with dx square minus y square and dz square. And accordingly we get this pattern of the splitting for tetrahedral geometry. So this dx square minus y square, dz square, which are along the axis, will feel less repulsion, that's why down. And these other three, dxy, dyz, dzx, their interaction is more and it will go higher. This is tetrahedral. Next is square planar. Square planar geometry also we have not discussed yesterday. Let's continue with the square planar geometry. First of all, you take octahedral to start with. Okay, so this is the plane. Now there is one point here, one point here. Now you join them with all the corners, and what we get? 8 different faces. One this way, this way, this way, and this way on the top, and from the bottom also 4 different sides. So total 8 sides are there. That's why it is called octahedron. So in this octahedral geometry, this and this were considered as Z. Others are XY. So this is the XY plane custom. That is a normal custom. That this is taken as the XY plane, and above and below you have the perpendicular one, that is called Z axis. Now you remove these 2 ligands from this Z axis. So this upper and bottom one, these 2 were removing, that is Z axis. So these 2 ligands from the Z axis we are removing. So what will be left to one will be XY plane. So that is square planar geometry. Whenever you remove 2 ligands from this octahedral geometry, top and bottom, from the Z axis you are removing, then we are living with 4 different ligands, 4 ligands, but it will be into a plane, that is the XY plane. That is square planar geometry. So in this situation, the orbitals containing Z will go down energetically, because the repulsion factor is removed. That's why Z related all the d orbitals will go down energetically. So dz square will go down. You can see here. So z square was here, it has come down. Z related all the d orbital levels will come down energetically. Why? Because the ligand is removed, so the repulsion factor is also removed. So dz square will come down, and it has come down. Along with that, xz and yz also will come down, because they are containing z. So xz and yz has come down. See here, xz, yz both have come down. So this is octahedral geometry converted to square planar geometry. Now, whenever you are removing 2 ligands from the Z axis, then the repulsion factor containing Z will be minimized, and energetically it will come down. So x square minus y square and xy, these will go energetically higher, comparatively higher. So this one is dx square minus y square, and this is dxy, they are comparatively energetically higher. The one that is the with containing z, actually dz square, dyj, dzx, they are coming down. So this is the ultimate geometry for square planar. this splitting of the square planar geometry. Okay, this is the splitting, CFSE splitting for the square planar geometry. So delta SP is highest compared to delta OCT. The splitting will be very, very high in this case. Why? Because in case of square planar, all the d orbitals are into the same plane, so they will feel comparatively more repulsive because they are all the same plane, so they are comparatively closer. Okay, they are comparatively closer and it will feel more repulsion. That's why the splitting, see the splitting here and see the splitting here. The bottommost and the topmost, if you compare, the overall CFSE has gone up. Maybe individual, the gap between the two is less, but overall geometry, if you see this dyz and dx square minus y square, the gap between has increased. Okay. This one energy decrease, so that's why there is a red color circle here given. So to mention that dz square has come down energetically, this dz square was here, it has come down here, and dyz dzx is more or less in the same place, not much changed, but these two are energetically higher, dx square minus y square dxy is comparatively higher, okay, and so on. This is square planar, so this square planar is having the maximum splitting, then octahedral, then tetrahedral. That is the relationship. Now, how we calculate the CFSE? Calculation of CFSE, crystal field splitting energy calculation. CFSE is calculated as the energy of the ligand field minus energy of the isotropic field. Isotropic field means before the complex formation, and this is after the complex formation. So this difference in energy, it is called the, so this is the isotropic field and this is the ligand field. Both are ligand field. So under the ligand field, so the difference is called the CFSE. The difference between this and this, that is called CFSE. So you can calculate the CFSE accordingly. Let's take an example. Here, well, so T2G and EG level. Now, this is minus 0.4 delta O and this is plus 0.6 delta O. Why I can explain it as a energy balance. This has come down. Okay, so how many levels? 3 levels. So minus 0.4 into 3, minus 1.2, and here it is plus 0.6 into 2, because 2 levels, that is plus 1.2. So actually it is overall energy balanced. Energy has gone down, energy has gone up, overall balanced. So that's why the plus 0.6 will be the upper part and the lower part is minus 0.4 delta O. Delta O means splitting energy for octahedral complex, that is delta O. So the CFSE is calculated accordingly. Now CFSE is calculated how many number of electron present, accordingly need to calculate. Now minus 0.4 into n T2G means number of electron present in the T2G level, and this is plus 0.6 n EG, number of electron present in the EG level. Okay, so here if you have suppose 4 electron, so all will be here. If it is a high spin complex, then it will go up, above, below and above. Total, suppose 4 electron total. So 3 electron go into T2G and 1 electron go into EG if it is high spin complex. Then we can calculate accordingly. So minus 0.4 into 3 plus 0.6 into 1. That is the calculation. Into delta O. Delta O is the total splitting energy. So into delta O you have to make plus MP. MP means number of paired electrons. Number of paired electrons. This is a general formula. Now with specific example we can calculate the CFSEs to make concept more clear. Let's go ahead. So this one, number of electron we are taking. So here what you have, minus 0.6 Ne means number of electron. This is for tetrahedral complex actually. For tetrahedral, T2G is above and EG is below. So accordingly, the upper one will be 0.4 or 0.6 and bottom one will be, no, actually upper one is 3 level, so 0.4 and bottom one is 2 levels, so 0.6. Otherwise how can you get the energy balance? Okay, So minus will be then 0.6 and plus will be 0.4 in that case, in case of tetrahedral. So minus 0.6 into number of electron in the Eg, because Eg is now down, T2G is above, plus 0.4 into in T2. But can you just note one thing, that there is no G here? Not supposed to be, because there is no center available, just like there in the octahedral. In case of octahedral, there is a barycenter, it is called barycenter. So that barycenter is present, but here in case of tetrahedral there is no such barycenter. That's why the G term is not applicable here. So that's why you are writing E T2 but not G. Okay. So number of electron you have to multiply, and this delta T, the tetrahedral splitting energy, is equal to 4 by 9 into delta O. That is a standard relationship between the tetrahedral and octahedral. So this is the way we calculate, and that we can make relationship also with the octahedral, because this is the relationship between tetrahedral and octahedral. So CFSE of tetrahedral, if you want to calculate and we can compare with the octahedral, then we can use this relationship and find out the formula. This is the general formula for tetrahedral with respect to octahedral. If you want to compare tetrahedral and octahedral, how much is more and how much more, which one is more and how much more, that you can do with the help of this formula. 4 by 9 delta O is delta T. So initially it was delta T, we replace that with the value 4 by 9 delta O, and we get this relationship. So after that, this 4 by 9 is multiplied, this multiplied here inside. So what we get, CFSE equal to minus 0.27 in E plus 0.18 in T2 into delta O. This is the actual real life calculation. Isotropic field 7 into 0. Why? Because isotropic field is actually your reference frame. That's why the energy is considered as 0. So those electrons residing onto these levels will be considered as 0 energy. So 7 into 0 plus 2p, because 2 paired spin is there. So that's why 2p. P is for pairing energy. So MP was there in the formula. So M is 2 here. So that's why in plus 2p. So this is the energy of the isotropic field. Now ligand field you need to calculate like this, minus 0.4 into 5 number of electrons they are here, and plus 0.6 into 2 into delta O plus 2p. So it is coming down minus 0.8 delta O plus 2p. Now CFSE will be calculated as ligand field minus isotropic field. So minus 0.8 delta O plus 2p minus 2p. So 2p cancelled, and we get CFSE equal to minus 0.8 delta O. This is one calculation. Just to have a look and try to follow. If you have any doubt, you can clarify here. I'm giving you some few second time. Just go through. If you have any doubt here, you can clarify again, and then only go ahead in the next topic. Could you understand how it is happening? How we are calculating? It's a matter of calculation. How we are calculating? CFSE calculation. Only telling about CFSE, talking about CFSE is not enough. Actual calculation, how much CFSE is happening, it is important. Why? Because from the CFSE calculation you can understand whether the catalytic property of a particular compound is suitable or not. So how much is the energy DD transition, how much energy will be required. From that you can speculate previously that what will be the color of the complex. We can speculate without doing the actual experiment. Theoretically you can give the idea, and after that you can verify with your experiment. Nowadays the procedure has become different. Earlier what people used to do, experiment was their random experiment, and after that theory was proposed to support the experiment. The theory was proposed. But nowadays what people are doing, initially not experiment but model is given, some model, theoretical model based on some AI model, AI ML model, okay, and then based on that we can speculate a lot of things, and finally you have to support it by experimental evidence. So nowadays experiment is coming at the last because it is costly. Experiment is always costly, and theoretical model is free of cost. If you have the software, you can do again and again and again. You can go on giving the trial without any trouble and without any cost also. So that's why this is the way now science is progressing. First you have to give the model. Have you heard the recent Nobel Prize in Chemistry? Recently there is a some model is given, and the model has got Nobel Prize. And that according to that model, if you actually implement some method, then maybe the global warming or the climatic condition changes that is happening, we are facing the problem recently, can be totally cut off. So according to that model, if you actually go ahead, then maybe in future the climatic condition or the problems that is we are facing now will be totally wiped out. The problem will be solved. So that's why the Nobel Prize is given. Model got the Nobel Prize, think over it. Not yet tested, but the model is so nice that it got the Nobel Prize. Now next is D7, real life calculation. See, total 7 electrons there, 6 here and 7th one is here. That means it is low spin complex, low spin. Okay, so D7 means cobalt, we can think over. Okay, so here minus 0.4 into total 6 electron and plus 0.6 into 1 electron. So that is calculated here. And isotropic field is just like earlier, and ligand field is plus 3p because 3 pairs are there here in the ligand field, 3p, but the isotropic field there is 2p. 2 paired was there, now there are 3 paired. So that's why p is not totally getting cancelled, 1p is remaining. P is the more or less fixed quantity and amount of energy that is required for pairing of electron. This is more or less fixed quantity. That's why this value can be known value. So minus 1.8 delta O plus P, that is the CFSE coming for a octahedral D7 complex, low spin octahedral D7 complex. You can calculate the CFSE and this is the final result of the CFSE. Now delta O, why the value is not given? Because the splitting will depend on the ligand that you are using. That's why specific value cannot be given. So general formula given, not the specific values. Because the splitting value will depend on the ligand constant. What ligand you are using. If it is cyanide, you get certain value. For the same D7, same cobalt. D7 is cobalt, right? D7 is cobalt. So cobalt as is D7 as example. Cobalt as CO2 plus D7. So 4s2 3d7. So if you remove 2 electron, it will be 4s0 3d7. So D7 means we can assume it is cobalt, right? So D7 cobalt complex. Now if you take chloride, you get some splitting value. If you get cyanide, you get some other splitting value. That's why the value specifically cannot be given. It is given delta O. It's a chart of the same type of formula, etc. Don't have to detail. You cannot remember also, that's why I skip these things. Okay. So I am showing you that this is the known thing and it is already can be charted like that. Now what regarding spin pairing energy, there is certain things to know, that Coulombic repulsion, why spin pairing will need some energy, why it is endothermic. There are two reasons. One is Coulombic repulsion, because 2 electrons if you paired up, they will be very close to each other, so they repel also because of electronic cloud, negative charge, both are negatively charged, so there will be some repulsion, Coulombic force of repulsion. That is there in the point number 1. Then point number 2, loss of exchange energy on pairing. Suppose you have some 3 boxes and you have 2 electrons. You can put electron 1 into box number 1, electron 1 into box number 2, electron 1 into box number 3, electron 2 into box number 1, electron 2 into box number 2, electron 2 into box number 3. So that way lot of permutation and combination possible. And this permutation combination is called thermodynamic probability, and accordingly some energy is released. It is called exchange energy. There are a lot of possibilities, lot of probabilities, and it is giving some sort of energy release because you have higher entropy state. When you have a very limited space, that it will lose the entropy, and otherwise it will gain the entropy, and gaining entropy is always spontaneous. That way, if you have more possible positions where they can be exchanged, that is more favored, and it is called exchange energy. For electron filling, it is called exchange energy term. So loss of exchange energy will occur if you pair up the electron. These two factors you will have to apply certain energy, give certain energy for the spin pairing. That's why it is endothermic. Now exchange energy term, it is calculated mathematically n into n minus 1 divided by 2, where n is the number of pair of parallel spin electrons. Okay, that way you can find out the exchange energy. Read the last line. Consider Fe2 plus D6 and Mn2 plus D5. In this case, Fe prefers low spin, whereas Mn prefer high spin, and that is explained by considering the loss of exchange energy. D6 T2G, if you fill up, all the 6 electrons will go into the T2G. There is no unpaired electron left behind. But D5 and Mn2 plus, it will prefer that low spin, high spin. That is because they have 5 electrons and 5 orbitals available, and exchange energy will be very high. So that's why it will prefer itself. I am not talking about the ligand field. Without any ligand, this will prefer, this Mn2 plus will prefer, because of higher exchange energy, it will prefer high spin. Whereas D6, this Fe2 plus will prefer low spin, because it can fill up itself in the T2G, and there will be no such exchange energy available, and it will not go into the EG because their CFSE will be lost. So both the way there is some pros and cons actually. So 6 electrons, 5 positions, 6 electrons. So one pair here. So in this case, high spin and low spin both are compared. So if you take high spin means this exchange energy is 10, value is coming 10, and if you take low spin, then exchange energy is coming 6. Compare formula n into n minus 1 by 2. So here 10 is missing, sorry, here 2 is supposed to be there, so it is missing. So actually it is a photograph, na? I cannot edit also. That's a photograph taken from somewhere. So now here total you have 6 electrons. So here you have 4 and 2, so that is high spin. So n into n minus 1, that is 5 into 5 minus 1. What is n actually? Just see, number of pairs of parallel spin electrons. Number of pair of parallel spin electrons. And here it is 3 pairs. So loss of exchange energy coming 10 minus 6, that is 4.
But sir, in high spin, how it is 5, sir?
5 actually here, see the n, the definition of a number of pairs of parallel spin electron, not paired. Parallel spin electron, actually parallel spin electron 5, because you see 1, 2, 1, half, plus up, plus up, plus up, plus up, plus up, 5. 1 is minus half, ignore that. See the following number of pairs of parallel spin electrons. They are parallel, na? 1, 2, 3, 4, 5. 5 are parallel.
Pairs.
No. Here this is this 1, 2, 3, 4, 5. These are all. This one, all are parallel spin.
But they are not
Same
pairs.
spin, same spin.
But they are not pairs.
No, paired not equal. Paired will be 0, na? Paired will be 0. They are 1, 2, 3. 1, 2, 3. 3 are there, and here 5 want plus of spin. Just count the number of plus of spins. Count the number of plus of spins. Ignore the minus of spins. So that way it is 5, and here it is 3. So here also paired, na? But here it is 1, 2, 3. Only plus up is considered. That's why 3, 1, 2, 3, 4, 5. All are plus up spin. That is considered. So this is here is 10 and here is 6. So that is 4. Here again you compare. Again 5. No change, you see. For this example you will also understand. Here also 3. That means doesn't matter. Paired or unpaired does not matter. Only those who are parallel spin, that is considered. Here it is 1, 2, 3, 4, 5. Here it is 3. Minus of spin we are not considering, only plus of spin. Because exchange energy means all should be in the same state. They can exchange among themselves. What I mean to say, okay, last one. This is paired, fine. But this can jump here and this can jump here. Or not. That also can give some exchange. This one you cannot exchange this and this. But this and this can be exchanged. That is the reason. Square. ও আচ্ছা আচ্ছা দাঁড়া 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 না 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 টু হবে টু 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 ওটা মনে হয় এই টুটা মনে হয় এখানে চলে গেছে আন্ডারস্ট্যান্ড দিস পার্টিকুলার টু অ্যাকচুয়ালি সাপোজ টু বি হিয়ার শিফট হয়ে গেছে when we take it from someone and paste it na sometimes this happens. I think this not square, this 1 2 has come down from here. This font size and this font size equal, just check. And this font size and this font size equal. So these two are supposed to be here. Understood the problem? It has come down, nothing.
Sir, for the low speed, in the denominator 2 will not be there?
2 will be there. Oh, that I am telling. For high spin as well, 2 spin, there will be 2. Below there will be 2. And
Formula will be same, na, sir?
same formula. Supposed to be. I'll try to rectify this. There is a mistake, so there can be confusion. But I'm clarifying the confusion. Now, supposed to be 2. There obviously will be 2. So in the next line it is 2. So how it is possible? Must be 2 there. Somehow it is missed somewhere. Now I think the concept you understood. So for low spin delta O greater than P, then only if delta O greater than P, then only low spin will occur, means spin pairing will occur. And if the delta O less than P, then it will not occur. Then it will be high spin. So that means it is a comparative study between the delta O and P. If delta O is higher, then spin pairing will occur, and if it is lower, then spin pairing will not occur. Then in that case it will be low spin or high spin. Accordingly, this is low spin, this is high spin. For weak field ligands, pairing energy will not be considered with CFSE. What is the meaning of that? For weak field ligands, pairing energy will not be considered with CFSE. For weak field ligands. Whereas with strong field ligands, pairing energy will be considered along with CFSE. Just with example, you can clarify that. This is weak field and this is strong field. Strong ligand, weak ligand. For this is H2O. So I think here it is there. Just see. So this is high spin for. Acha, here pairing energy is not considered. Why? And here pairing energy is considered. Why? Why? The reason is, in case of high spin, for weak field ligand actually, for weak field ligand like water.
Sorry, concept in place?
No, for weak field ligand actually what is happening, there will be always high spin. So that whether you calculate delta P or not, there will be always high spin. That's why not calculating. There will be no question of high spin, low spin. For strong field ligand only there is a question of high spin, low spin. But for weak field there is no such. That is not possible. It will be always high spin. That's why you are not considering the delta, that P value, the pairing energy. For strong field it is calculated, but for weak field it is not calculated because it will be always high spin. There is no question of low spin and high spin.
Why, sir? Why?
Low spin means delta O is low. It cannot pair up the electrons. Never it can pair up the electrons. So always for your weak field ligand, always it will be low spin. High spin. Always it will be high spin. So pairing of electron is never happening. So what is the point calculating? Because if there is a two possibility, then you are calculating and finding out that whether it will be low spin or high spin. But for weak field ligand, there is no such possibility of low spin and high spin. There is always will be high spin and never low spin. Then why to calculate? So here this particular topic is completed.